So I'm Chun-Hao. I'm a postdoc at U Chicago. But today I'm going to talk about something that's slightly different than what you have already heard in this conference. So we use these simulations for validating our survey analysis and also use it to plan future survey analysis instead of using it for inferences. So I would think it's an easier goal, but I'll show some of the challenges that we are meeting right now, and I'll give some of the examples. So everything I talk today will be covered, actually not everything, most of the things will be covered in these two papers. The third paper is here because I just want to briefly advertise it. So the whole reason we do this, I do these simulations is because I want to use it to enable a joint analysis of galaxy cluster abundance and galaxy clustering and weak lensing. And this is so we have done that for the darkening survey, but this paper is actually the latest version of that. So we basically combine the SPD cluster abundance with DES 3x2 points and get some of the interesting cosmological constraints. Okay, so back to the talk. We have heard, sorry, doesn't work. Okay, so we have heard from many of talks, I think on Monday and Tuesday, and also today, that we can get some of the data, that's the mass map from this lensing survey, and we can apply some of the interesting tools like machine learning, wavelet scattering transform, or higher order statistics to get interesting cosmological constraint that's better than the traditional two-point correlation functions. But here I just want to remind everyone, this is actually not the data we see. The data we see is the next slide. It doesn't work. All right, this is actually the data. So this is actually what we observe. This is that. And there are actually a lot of steps to just go from here to here. This is actually already a very simplified version of this, but there are like many steps about this. So first, we need to select the galaxies that we want to use. Then for those galaxies, we need to measure their shear. And once we measure the shear, we also need to know their distance, right? So we need to do photometric redshift estimations. And once we have that, then we have to do map mapping, etc., to finally get these mass maps. This is just one example. Another is if we want to get a galaxy density map, we also going through a similar process, right? So we also need to select the galaxy we want to use. We need to estimate the distance, but also we need to have some way to mitigate the basis estimated. And this is just because some part of the sky will just be bright, and we just see less amount of galaxies, and we need to correct that. And then once you do, sorry, I don't know how. Once you do all of these steps, then you get the galaxy density maps, right? I should say a lot of these steps in the survey analysis are actually validated for two-point correlation functions, but not the higher order statistics. So before, it was just my cartoon version of how this works, and this is actually the more complicated plot produced by the darkening survey collaboration, trying to say how we get from the image to get the final cosmological constraints that we produced. Today's talk, I'll basically just focus on this tiny box called mark analysis, and you can see there's only one error that informed the analysis choice and modeling, which is actually not true. This is actually being used to validate a lot of methods in our cosmological analysis, this including developing the redshift estimation code, etc. This -9 is because this is actually happening in year 6, but not year 3, that we also use the simulations to generate some of the image simulations. Okay, so before I show some of the examples, let's think about like what are requirements for this kind of simulation, right? We want to use it to validate our analysis. So first of all, we want to use it to demonstrate that the accuracy of our model actually meets the precision of our measurements, right? So we don't need to throw a lot of data just because our model is not good enough. We want to use it to facilitate the development of the method in cosmological analysis. we also want to use it to help plan and design future surveys, and use it to estimate some of the impact of our decisions on our final cost module constraints. With this goal, what are the requirements? First, we really need, and then I'll give two examples, one on each of these, one on DES and one on the Roman high-altitude imaging survey. Okay, so the first requirement is we really need very accurate small-scale modeling. I think we have talked about like how the lensing is sensitive to small scales, but it's always in Fourier space, and I actually think about everything in real space, so this is just a real space version of that. So this two plot is the real observable. So this is side plus, side minus. So this is the two decomposition of cosmic shear signal. And this is just for the highest ratio beam for DES ES3. So what we did is just do some theory calculations. And in this theory calculation, you can just say, OK, I remove all our theory below 10 megaparsec. Then you get this blue line. And you can start to include smaller and smaller scales. From blue to orange include 5 megaparsec, including 1 megaparsec to 0.5 megaparsec and to 0.1 megaparsec. And you can see that you really need to include stuff below 0.5 megaparsec to actually be within 1 sigma of the just within the DS arrow bar, right? So this is actually saying that our lensing measurements are actually sensitive to very, very small scales. It's actually very deep into the 1 Hz region. This is just for lensing. For galaxy, the same thing is actually the same. So the left-hand side, this is the galaxy clustering measured from SDSS. So the dot with the arrow bar is the measurement. The color line is our new version of the simulation that we call cardinal. The gray line is the buzzard. So this is the previous version. And I just said this is actually plotted in linear space, not the log space. So it will actually looks much better in log space. But here you can see that there's a tiny difference actually between the cardinal and buzzard at a very, very small scale. So at a 1 megaparsec region. And you might say that this like phenomenologically looks like OK. But these two models actually produce very, very different amount of galaxy clusters. And it's actually by a factor of 2. So on the right-hand side, it's just comparing. So we run through the whole DES cluster finding pipeline and really compare what the cluster we get in the simulations and what the cluster we get in the data. So the one means that we actually get the expected abundance from the data. So the red line here is from cardinal, so it's corresponding to this color line. And the gray line actually is buzzard, so it's correspond to this gray line. Right? So you can see this tiny difference in the small scale clustering actually causes a huge difference on the observable, and it's actually by a factor of 2. So we really need accurate small scale galaxy clustering. Okay, I have to be a little bit faster. The second requirement is that we really need large volume. And again, you can actually also do some theory calculation. And in this work, it will just do a very simple Halo model calculations. It's actually collaborating with Shifang, who is using this for baryon applications. But the idea is the same, right? So you can just break down your signal by contribution of different objects, right? And in Halo models, you can decompose everything in the 2 Halo term and 1 Halo term. And in the 1 Halo term, you can decompose stuff by the Halo mass. So the pink one is that you only have halos above 10 to the 14. And you can see it makes a lot of powers. But once you include the halos with the 10 to the 13.5, you can see that you already bring the curve within the arrow bar of the DS, right? So this is actually saying that this massive object actually play a significant role or contribute a lot in our overall lensing signal, right? And these objects are very rare. So if you only have a very, very small box, it's very hard to capture the physics in those rare objects. Okay, So the third thing is actually a little bit, I think, less appreciated, but I just use this toy example to demonstrate why this is important. Is that we not only want one realization of the full survey volume, which is already super hard, but we really want at least 10 realizations of the full survey to actually make meaningful conclusions, like whether our systematics, so whether the precision in our model actually meet, the accuracy in our model actually meet the precision of our measurement. So let's say you are trying to infer the value of these two parameters, just very simple examples, right? So it's like x0 and x1. And we know none of the analysis is perfect, so there is some tiny systematics, 0.3 sigma. And you want to say whether this systematics is smaller than my statistical power of the measurements, right? So if you have perfect simulations and there's no noise, then you will get something like this, right? So you get you just run your analysis and you see your posterior is shifted a little bit to the right because of systematics. However, your simulation actually have noise, right? So if you just have one realization of your observations, then you'll get something like this, right? So you just be randomly shifted by your noise, right? So if you only have one realizations, then you'll get something like orange one, and it's very hard to make assessment that whether our systematics actually bias this actually in which directions and by what amount, right? But if you have 10 realizations, they will get something like this, and you can combine all of them and say, make some statistical statement that what's your confidence that the systematics in your model actually is smaller than the statistical uncertainties of your measurement. Okay. Okay, I talked about all the requirements. So we really need accurate small-scale modeling. We really need large volume. And we really need many realizations, right? So this actually means that we need large volume and high resolution. And it's basically almost impossible unless you have the Argonne computers. It might be possible. But we don't have that so far. So what we did is we do some kind of pair simulations with high resolution unbodied simulations, actually all unbodied. So it's like high resolution simulations where we can do some of the traditional techniques to paint the galaxies. And what you can do is just you write down some analytic functions. We don't even use machine learning, so we use analytic functions that's based on some of the local density and the distance to massive halos to learn some approximate way to paint the galaxies in a low resolution light cone simulations. Okay, I probably don't have time to explain this, but yeah, we just pair the two simulations and use that to paint the large volume, high fidelity galaxy catalog. And because of this, and we can basically run, I think the nice thing about these simulations is that we actually run a lot of survey pipeline on these simulations. So we basically run the whole photometric redshift code in the same way. It's basically the same way as it's been run on the data. And because of that, we can actually do select the galaxies in the same way as being selected on the data. So this here is basically just showing you the source galaxy catalog, the lens galaxy catalog, and cluster catalog, the redshift distributions, especially for DS-ES6. And the dashed line and the solid line are the true redshift and the photometric estimations, right? Okay. There are two examples. I probably don't have time to talk about all of them. I'll spend 10 seconds for the first one. So you can actually apply this on DS, and then you can say this is for year 1, this is for year 6. That this is the final result, and this is then we can recover the true answer. But I really want to talk about Roman. So we also use these simulations to inform some of the planning for the Roman survey. So the idea is that we got like some of these questions from I think from some of the committee in NASA that like what should be the deep what should be the size of the field of our survey and what should be the depth, how many bands do we actually need, what kind of SPECS sample we actually need so we can deliver the cosmology that we claim that we are going to deliver. So to answer these questions, we actually run a Roman type of the cardinal simulations with LSST photogrammetry, so this actually have the footprint dependent noise, and with the Roman observing sequence that basically say like this telescope point to this part of the sky at this time of the year, etc. So some of the preliminary studies saying that if we just have UK like SPECS, then because photometric uncertainties, then we get basically more than one sigma bias in SA. In these studies, we basically find that we really need this kind of the spectroscopy samples for some of the unbiased cosmology for these specific configurations. So we actually make some recommendations on what should be the limiting magnitude of our survey to actually have a realistic spectroscopy sample to get the unbiased cosmology. Okay. I don't have time, but just leave a conclusion here, saying that we really need these three requirements for this simulation to be useful. And I basically talk about two example applications, one for DS and one for Roman, and I'll take questions for now.
Questions? Yes, Jonathan, you're always.
Since you were running out of time, I was curious if you could say a little more about how the high-res and low-res simulations are paired with each other, like how you take the high-res information and actually put it on the low-res simulation.
So what we did is that so in the high resolution simulations, we calculate some of quantity that's I said is the local density actually in Lagrangian space. So that quantity actually can be measured in the lowest resolution simulations, right? We cannot measure halos, we cannot resolve halos, but we can measure the local density of each of the particles. So what we did is that we learn the galaxy property related, how the galaxy property related to that local density. And you have the parameterized functional form of that probability distributions. And you use that learned probability distribution in high resolution simulations on the low resolution simulation to pen the galaxies based on the particles.
So you do sham on the high res simulation and then use that to learn this analytic relationship for the low res.
Yeah.
Okay.
A plot showing the S8 shift depending on your limiting magnitude. Do you think that's one of the reasons of the current S8 tensions, or what's the
that's not
implication?
Because in DS we specifically make a manual cut so that we know the SPECS. Actually, we don't even use. Wait. So we make a manual cut so that we make sure that the redshift training sample that go into our redshift estimations is not hugely biased, right? There's still some bias, but we actually marginally over that. But we actually have a specific manual cut for that.
Okay. Thanks.
So your method, aren't you worried that you might miss some like small scale clustering that you cannot map between these two? I mean, your low resolution simulation doesn't have the small modes, right? So wouldn't I be worried that if I have some systematic, say, blending that requires knowledge of like the small scale modes that I wouldn't be able to find these just by running this kind of validation test?
Yeah, that's a very good question. So I think that can be a potential problem. We don't measure that every step of the survey analysis. But I think one thing we check is that the small scale clustering is more or less correct. I don't think we actually go to the blending scale, and there might be a problem. We don't do like real image. We don't put the image on the simulations, right? So the blending will not be tested. So that should be tested other ways.
Any other question? So if not, thank you. Thank you very much again. Chris.
Can you hear me okay? Great. Okay. Yeah, so I just want to first off thank the organizers for inviting me. It's been a really amazing week. Nice to see some familiar faces, but also learn about all the new exciting stuff happening. I was originally going to just talk about CAMELS, but there's been a lot of discussion this week about this sort of volume problem with cosmological simulations. So I'm also going to talk about a related project called FLARES I've been working on for a few years. I put too many slides in, so let's get on with it. So a key goal, to sort of set the scene here of cosmological simulations of galaxy evolution is to simulate a representative population of galaxies that includes all of the physics that we need to simulate these objects at the required scales. And so in order to do that, we need really large volumes to capture all of these different environments, clusters and voids, high resolution, that's in terms of spatial mass and temporal resolution, and also all of those required physics, so the hydrodynamics, magnetic fields, the impact of cosmic rays, et cetera, et cetera. And ideally, we want to also compare apples to apples, so we want to forward model the observables from these objects and compare them directly to what we capture from our telescopes. And finally, explore the dependency of our results on these astrophysical and cosmological parameters. Now, clearly, it's computationally infeasible to achieve all of these things simultaneously, so we need to make compromises along some of these different axes of merit. So I'm going to talk about two of these today, so this sort of volume resolution trade-off, and also how we incorporate forward modeling and increase parameter spaces. So this is a figure of merit on the left, kind of shows where a lot of these flagship simulations lie in this plane. So there's this general anti-correlation between the resolution along the x-axis that you can capture and the volume that you can actually simulate. And you'll notice the 2 points here in red are the CAMELS simulations, but sort of lie off this relation due to the fact they're able to explore this large parameter range. And so, if we look at the actual, what we measure from these simulations and where that lies in the physical parameter space, these high-resolution simulations are able to probe these very faint objects that we're probing now at high redshift with the sort of JADE survey on JWST. Whereas if we want to probe the sorts of very rare objects that Euclid is going to find, then we need the large volumes to capture these rare environments. And so, again, just to sort of make this point really clear, so this is the fiducial Eagle 100 megaparsec simulation compared to the approximate volume probed by the Cosmos Web Survey around redshift 6. This is the combination of all of the cycle 1 proposals with JWST to sort of show that we're still sort of in the right sort of ballpark in terms of volume. And then this is Euclid-wide, right? So we're clearly in a very, very different volume regime here. And using these sorts of periodic simulations at this resolution is clearly not able to probe the sort of things we're going to find with Euclid. So zoom simulations, that's the sort of solution that I'm going to try and sell to you today. So we can take a region of interest from a much larger, low-resolution, dark matter-only box, resimulate this at higher resolution with all of the added physics that we need. And this essentially then also still includes this large-scale structure and the large-scale modes of the density of the matter power spectrum. So FLARES is this horrible acronym for this, but this is a project that's focusing on high redshift. And essentially what we do is we take a 3.2 gigaparsec dark matter-only volume compared here to Eagle and the Blue Tides volumes. And what we do is we measure the overdensity distribution in this box. So this is in log space. It's got this nice log normal distribution at redshift 5. And what we do essentially is we select objects at a range of different overdensities. So we're selecting both underdense objects here as well as very, very overdense objects. And you'll notice that we're kind of biased here to the most overdense as well. This is what they then look like. So these are spheres around 20 megaparsecs in radius. So when I say zooms here, I'm not talking about the sort of DREAMS approach where we're simulating individual objects. These are relatively large cosmologically representative volumes. So the total volume of this is sort of comparable to a single sort of 100 megaparsec periodic simulation. This is going now from like sort of the lowest overdensity to the highest here. And then what we can do is we can then sort of combine these together statistically, right? So say we want to measure the composite stellar mass function across this whole 3.2 gigaparsec box. So what we do is we measure it in each of these regions. So this is the stellar mass function from this very overdense region. Here it is from the most underdense region. And here it is for one of the mean density regions. Now what we can do is we can apply a weighting to each of these based essentially on the ratio or the relative abundance of these objects in the whole box, right? So sort of the ratio here between this black line and the blue line. And then essentially we can just linearly combine these together and we get out a composite galaxy stellar mass function. So on the left is the Eagle 100 megaparsec volume, and you can see that we don't really probe this sort of this tail of the Schechter function at these redshifts. And on the right is flares. So we're able to clearly distinguish this nice double Schechter shape and probe these very rare, massive objects at high redshift that are going to be probed by the largest surveys. And this is just pre-JWST to show that it's not rubbish. It does knit them data. So yeah, again, to sort of like really hammer this home, we're now in this regime of this sort of large volume boxes. And we essentially, what we're doing here is we're extending this axis here on the y-axis up into this sort of target parameter space where we can probe the Euclid deep and wide surveys, but at the sort of resolution we need to find some of these very faint galaxies. Now, flares, as I think, has been a really successful project and has been used now to compare to a lot of JWST surveys. How do we push this down to lower redshift is sort of an unanswered question at the moment, and how do we do this for large ranges of parameters? So we're actively exploring this, trying to answer the question of how many regions do you need to achieve a certain level for a given simulation. Which number is it? Okay, it's that number. Okay. Oh my God. Okay. Okay, so yeah, so like, how many regions do you need? How big do those regions need to be? And how do you actually capture, say, 10 to the 15 solar mass clusters at redshift 0? Do this in a properly statistical way to really probe this down to low redshift. These are unanswered questions, but we're trying to answer them now with the flares group. So please, do stay tuned. Okay, so flares, we get these sort of discrete volumes within this much larger space. But obviously, if we want to measure something like clustering statistics over this continuous box, then we can't do that with these zooms, right? So we need new techniques to try and cover this space and maybe use these zooms for this. So what we do is we essentially model the galaxy-halo relationship, which we heard a little bit about today already. This is a slightly separate project. This was using the cluster eagle simulations at lower redshift. But essentially, we use a very simple machine learning sort of tree-based model just to learn what kind of galaxies live in what kind of subhalos based on their dark matter properties. And so we can then use that to reproduce the galaxy stellar mass function out to much larger densities. But the most interesting thing we can do with this now is we can apply this to this much larger dark matter-only box and measure clustering statistics. So we can not only measure these down to very, very small scales because of the higher resolution, but we can also extend out to much larger scales as well. So, and the third thing is we can then measure these clustering statistics also for much larger or more massive galaxies. So this is a way of taking these zooms, learning something interesting about the galaxy-halo relationship, and then being able to test these simulations in this sort of large volume regime. Now, the problem with these sort of tree-based models, they're fully deterministic. So you get a single galaxy given a set of input dark matter properties. So you end up actually under-predicting the scatter in some of these distribution functions, right? So what we need to do is look at new methods where we can actually capture this scatter in a more efficient way. And we've been exploring sort of normalizing flows or density estimation techniques for doing this. This highly complex figure here is just a way of getting some halos as well. So not only do we model the galaxies that live in halos, but also the density distribution of those halos themselves. And we can do stuff like this. So we can essentially create a set of halos for arbitrary cosmological parameters. We can then populate those with galaxies, taking into account all of the covariances between these different physical parameters, and explore things like the galaxy stellar mass function, star forming sequence, etc., as we change those parameters. So this is, again, it's sort of a work in progress, but I think there's some quite exciting applications of this. So we're mostly done, right? So we've got large volumes. We can go to high resolution. We've got most of the physics, so yeah, the TNG people will tell you need magnetic fields, but yeah. We've got rapid forward models now for inference. So the last slide I showed, we can rapidly generate these populations of galaxies and use these within inference pipelines. So the last sort of missing piece here is the forward modeled observables. And to motivate this a little bit, I've got this figure of merit here, which sort of summarizes kind of what we're all trying to do, right? We're trying to compare our physical theories to observations, right? And maybe, I should probably use this, shouldn't I? Here we go. What we typically do is we go from right to left, right? So we identify some sources in our observations, and we apply spectral energy distribution fitting to these to obtain some physical properties. And this is typically where we do this comparison between theories and observations. Sometimes we do some phenomenological modeling just to go straight to the physics here, but this is the kind of the most common space where we do this comparison. Now, we've heard a lot from different people in the room about how we go the other way, these blue arrows. So we take some physical theories, we run numerical simulations, whether they're sort of gravity only or hydro, to obtain some fields, the dark matter or the matter density distribution or some hydrodynamical fields. And then what we do is we apply some structure finding or semi-analytic methods to those to get the physical properties out where we do our comparison. What's less frequently done, obviously a lot of groups are working on this, is to fully SED model the galaxies into their observational space and allow us to do this comparison here. And even more rarely do we do the full pipeline right to the observational field level, right? Which is obviously much more necessary for things like line intensity mapping experiments. Now, there's no right way to do this comparison. I think that's the main point I want to make. There's value in doing different approaches, and they will reveal different biases in the way that we do this modeling. But I think there's also a lot of limitations to the way that we do this SED modeling step, for example, and do it in a consistent way with this SED fitting step. So this is part of the motivation for Synthesizer. So Synthesizer is designed to be a code for producing synthetic observations from simulations. And I've been working on this for a few years now with Will Roper and Ashwin Vijayan, who are both postdocs at the University of Sussex in the UK, and Steve Wilkins. And yeah, it's been a huge amount of work. It's all public. It's a Python code for doing this sort of stuff with a lot of the heavy lifting sped up in the background. And the main sort of philosophy, I guess, with Synthesizer, to distinguish it from other codes that you might have heard of, so dust radiative transfer codes like SCIRT and Powder Day. Synthesizer isn't a dust radiative transfer code. It's meant to just be a very fast, flexible, modular, and extensible code. And what I mean by that is, we try to accelerate things to allow you to get from zero to some observed property as quickly as possible. And that then allows you to test some of the model dependencies. So things like, what dust model did you assume? What stellar population synthesis model? Different aspects of the photoionization modeling. So the sorts of things that typically you choose right at the start of your analysis and never explore your model dependencies on. Water. Okay. I'm really sorry about this slide. So yeah, Synthesizer wasn't meant to be this big, but things got out of hand. This is already out of date, but essentially it's to try and give you an idea of the stuff that we're trying to do with this, right? And the modular part of this then becomes important, right? So we're not rewriting or reinventing the wheel every time, right? We're trying to use these different components in a self-consistent way to allow extensible features. But essentially, yeah, you have things like SPS models, you have AGN models as well that have all been run through photoionization codes. You can generate SEDs, images, IFUs, etc. There's a range of different dust attenuation curves. You have the ionizing emissivity that you can calculate directly. You can run line-of-sight attenuation models, so you have variable optical depth depending on the 3D star dust geometry, dust emission with some PAH features, imaging, complicated star formation metal enrichment histories. We have a concept called emission models, which essentially allow you to combine together all these different things in quite sophisticated ways, depending on what modeling you want to do. IgM transmission, SEDs with photoionization codes like Cloudy run on them to predict the nebular emission, AGN emission, which is horrible. You can then create things like BPT diagrams, line ratio diagrams from these. We have a connection to the SVO filter service, which allows you to then generate broadband photometry for arbitrary instruments. IFUs, so we have IFU functionality, and this is sometimes a GIF, but apparently not today. Abundance patterns that you can change in the photoionization modeling, another spectrum. And then, yeah, you can make your unknown pleasures, synthesizer cover if you want to. So yeah, that was just to, again, I apologize. It's just to make the point that it does a lot of stuff. But what we've used it for most recently is to model the broadband photometry across all of the CAMELS simulations. So we've basically used a lot of the functionality I've just shown you to predict the intrinsic and dust attenuated spectra, and then post-process these with a range of different UV to near-infrared filters. We've done this with two different SPS models, BCO3 and BPAS, which includes binaries. We're using a shallow and full 2000 dust model, so this sort of over-attenuates very young stars. And we generated the rest frame luminosities and also the observer frame fluxes for all of these objects for 34 snapshots out to redshift 6. So this is a lot of galaxies, so around 200 million sources. And nobody's emailed me to complain yet, but I think this is the largest set of synthetic photometry from a hydro simulation suite created to date. And I imagine there's probably somebody in the room who will tell me I'm wrong, but that's fine. So this is just an example spectrum for a given galaxy, showing the attenuation curve that we assume. This is a Milky Way-like attenuation curve from the 2008, and some of the broadband filters that are used. So this is all now public, so you can go onto the CAMELS website and download this photometry and start using it for your science. So what does it actually look like? So this is just the CV set, so the combination of the 27 CV set simulations to sort of nail down some of this variance, but showing the differences between the four different main sort of CAMELS simulation sets. We have the full AH set for at least. So you can already see there's some quite big differences here, right, between some of these simulations. So Astrid tends to have a slightly lower normalization in the optical compared to some of the other simulations. But some of the most drastic differences we're seeing are in the colors. So these are the far UV to near UV color distributions, as well as some optical distributions. You can see that Swift Eagle and TNG tend to have this more bimodal blue and red populations, whereas Simba and Astrid tend to have this more sort of unimodal distribution here. So there's already a lot of interesting stuff here, just the comparison between the simulations at the fiducial parameters. And then you've got, redshift evolution as well of these parameters. And then obviously the most interesting thing is to now start digging into these parameters. So what happens when you change omega matter? You kind of get what you might expect, I guess, in the optical. So the top row here is the UV luminosity function. This is a little bit more noisy, essentially because it's more sensitive to very recent star formation that might not be sampled as well. But in the R band, you see there's this nice smooth evolution in these distributions. You might notice there's also some degeneracy. A very high omega M, you don't actually see a huge impact on the R band luminosity. But the most interesting thing, I guess, is these colors, right? So as you go to higher omega M, you actually get redder color distributions. And just to separate out the luminosity evolution here, so as you change omega M, obviously you're getting more halos. So maybe that's just what's driving this. We can look at the mass to light ratios. So at fixed subhalo mass, we find that for a higher omega M, you actually have brighter objects in both the UV and the optical. So it's not just more halos, therefore more galaxies in your selection, but actually galaxies are brighter. These are horrible plots of sigma 8 and ASM1. Even on this screen, they're not great to look at, sorry about that. But essentially just trying to make the point that, there's obviously a lot of very complicated covariances between these parameters and the emissions. I'm going to focus mostly on one here. So one of the things that I guess was most surprising, which is that when we change sigma 8, which controls the clustering of matter, we actually find very big differences in the color distributions. So the luminosities tend to be sort of insensitive to this, but actually as you increase sigma 8, you get much redder objects. And when we looked into this, we found that when you increase sigma 8, you tend to get galaxies forming much earlier. So galaxies are older and therefore redder, and so that's how this sort of this color effect manifests. You also get a slight secondary dependence of the metallicity, so things tend to have higher metallicities when you increase the clustering. So obviously, once you've got all of this, you can run it on the LH set, and you can do inference. So we use the LTU ILI pipeline that we've heard a little bit about this week from Chun-Hao and others. And we basically use neural posterior estimation with some relatively simple setup to try to infer these parameters from the combination of the luminosity functions and the color distributions in the UV and optical. And what we find on this sort of like held out test set is that we do reasonably well, right? So we were able to constrain the supernova feedback parameters very, very well. Omega M as well has a really nice correlation, and obviously some tentative constraints on sigma 8. AGN, no dice. And then this is now for across the simulations. So these sort of results are actually consistent in the different simulation sets. Spoiler, doesn't generalize. So I've been really interested in a lot of the domain adaptation and domain generalization talks this week. And yeah, we'd love to speak more about this to try and find areas of this feature space where these results are invariant. But now we can start to do some interesting tests, right? We can ask, okay, what's actually driving the good constraints? Which colors, which luminosity functions? And so these corner plots are showing sort of 2 test examples of this. And you can see that the blue contours here are just using the UV and optical luminosity functions. And the orange is what happens when you just have the colors. And you'll see that it's the colors that drive the really good constraints on omega M, which I found kind of surprising. Now, when you go back and look at the 1P set, it's actually kind of obvious, right? There's these degeneracies there. But it's, interesting that just with colors, no abundance information whatsoever, just the ratio of red to blue galaxies, you can get these constraints. And also, we can do things like what happens if we measure these distributions at higher redshift and combine them together. And we find, if we switch to the next one, these are stacked posteriors. So essentially across the test set, so where they're more peaked, it means that the constraints are slightly better. And you'll notice here, so you can see more clearly here that the colors are what drive the good constraints on omega matter. We also find that, for sigma 8, we actually get slightly better constraints at redshift 2, which I really don't understand. So if anybody has any ideas, that'd be great. So we're done, Now, obviously, there's an awful lot of work to do to bring all of this together in the same sort of framework. But I think there's definitely scope in the near future to do something, really, really interesting, to really probe these very large volumes at very high resolution using zooms, include much more of the physics we really care about. And obviously, using a lot of these accelerated models and things like synthesizer, we can actually go straight to the observer space and start to really, really probe this. So I'm going to finish up just by advertising a workshop on simulation-based inference. There's lots of very beautiful people in this image that you've also seen around the room. So this will be in May. Abstract submission is open, so come speak to myself or Soteria if you're interested. Here's the to-do list, and I'll finish there. Thank you.
Thank you, Chris. Yeah, we have time for question. Tom?
Wonderful talk. So I've been talking all week to people of doing exactly the opposite. So starting from the images, building 3D models. And I'm wondering, I just want to see your reaction of how to think about doing all your synthesizer the other way around.
Just do it. Yeah. No, so maybe adjacent to what you're saying, but if I go back to that plot actually. But what we'd like to do is, and we're already working on this. Oh my God, I've got to go. Okay, there we go. Yes. What we'd like to do is to build this SED fitting code into synthesizer, and the idea being that we can use all the same components and do this really rigorously, with exactly the same framework, so the same SPS model, the same dust, et cetera, et cetera. Do it with traditional methods, but also using simulation-based inference methods, and that'll help to reveal some of these biases. But I don't know, so much about the.
Yeah, in fact, there are fully differentiable ray tracers now that are, I think, the ideal piece is exactly for that.
Amazing, yeah.
Very nice talk. I would like to ask about the first part. When you do the zoom-in region selections, what the volume is that? You didn't mention that, right?
Say again, sorry.
The zoom-in volume. How large is the volume?
Radius is 20 megaparsecs.
20 megaparsecs.
For each of the regions. So so we have 40 regions each, radius 20 megaparsecs. That's at redshift 5. Now, the nice thing of doing this at high redshift is that things are relatively linear at those redshifts. Now, as soon as you go below that, you get all these non-linearities, obviously, and the volumes become quite difficult to define. So that's why we focused on sort of high redshift for the moment.
Ah, okay. So I was misunderstand. So this different over density regions is based on the redshift 5 result, right? Oh, okay. So have you wondered that or would like to see that how this evolve down to redshift 0, how they look like, how they distribute, things like that?
Yeah, I mean, work in progress. Yeah.
Okay.
So, so we, this is early work at the moment, but we're basically using the flamingo simulations that we heard a bit about before, and seeing how we can, what kind of selection we can do, and what kind of weightings we can apply to reproduce the redshift 0 halo mass function, for example, and then using this to see if we can push down to this kind of redshift. Now, it becomes really tricky when you have 10 to the 15 solar mass clusters that require much larger volumes. How do we combine zoom simulations of different volumes? We're working on it, yeah.
Okay, great. Have you wondered, sorry, just one more. Have you wondered there is a BIOS when you push down to 0, right? It's selected at redshift 5, but you push down to redshift 0, there may be some BIOS and you have to take into account, right?
Yeah, so there's a different interpretation to bias here, but in terms of the weighting that we apply, so at redshift 5, we assume a single weighting and then apply that to all redshifts higher than that, which I think is reasonable in the linear regime. Now, obviously, at lower redshift, that's not the case. So we have been working on a weighting scheme that basically uses the density at that particular snapshot, so and essentially weights every single halo rather than weighting the entire region.
Okay.
Yeah, and that's one way of getting around this issue at lower redshift.
Okay, good. Thanks.
Spectacular talk. I have questions about the, so it wasn't generalizing well, moving between CAMELS volumes. Do you have any sense of why, or if there were places where it really failed? I guess the thing that came to mind when you mentioned that the colors were the thing really guiding the constraints, like, was there any sign of, like, if they have matched color distribution, if they both have the bimodal form, they did better? Like, tell us more about that.
So one of the tests we did was to reduce the fidelity in the color dimension, right? So, all the way down to just like how many red galaxies, how many blue galaxies, right? Hoping that this would, lead to some better overlap, I guess, in the simulation space. Unfortunately, everything was still very distinct. So even, I think we heard earlier this week about, this approach to reduce the fidelity at the field level when you're doing trying to figure out what you can get away with in terms of fidelity. It doesn't seem to work in these spaces, which I think is both a problem, but also highlights that this sort of galaxy formation physics has a huge impact on these star formation metal enrichment histories, and actually they're very, very discriminating. Yes, I don't really have much of a better answer than that, really. It's a bit scary, but hopefully we can find some way of generalizing.
Right. I love the talk, and I already love synthesizer. And as someone who will be giving it to students and other people to use, my question's a bit on the philosophical side. So, like, if you have thoughts, I'd love to hear it. With any model like this, you have so many free/tunable parameters, and it will, depending on the science case, depending on what you're going to use it for, you'll need to make certain choices. Do you plan to provide to the community like a set of best case choices when you don't know much about the problem?
Yeah, it's a short answer. There's a few examples on the documentation of like how to go from 0 to some forward modeled photometry for a given simulation. So I didn't mention we've already written front ends for all of the sort of major sort of fiducial simulations and also all the CAMELS ones, so you can go and have a play around. For things like the photoionization modeling, there's obviously a huge number of parameters that can go in there. So we provide some grids that have already been calculated of these SPS models post-processed through the photoionization codes using some fiducial parameters. Now, if you're really interested in the photoionization side of things, you can go in, make your own grids, change whatever parameters you want. But for most users, yeah, the fiducia will be fine. So we provide all of those for people to download and sort of get up to speed quickly. Yeah.
And last quick question. So if not, thank you, Chris, again.